our study of inferential statistics, where we're using sample data to make inferences or draw conclusions about our overall population data. So when we do, this is called actually hypothesis testing. So we will look at hypothesis testing in Chapter 8 and Chapter 10, and a little bit in Chapter 9. But all of this is inferential statistics. Remember the difference between inferential statistics and descriptive statistics. Descriptive statistics, we were describing our sample data. Inferential, we're using that sample data to draw conclusions about the overall population. So when we talk about hypothesis testing, we're going to have both what's called a null hypothesis, sometimes we say H0, and an alternative hypothesis, which we call H1. Some books will use a subscript of A here, but ours uses H1. So the null hypothesis is something we assume to be true, and the alternative is what we're trying to find enough evidence to prove. So oftentimes in the classroom, I compare hypothesis testing to our legal system. If, let's say, I was suspected of stealing a candy bar, okay, and I'm just using a simple example, and I went to the courtroom, and I go before the judge, and they ask me, how do you plead? Well, I either say guilty or not guilty, right? Because remember, I'm assumed to be innocent until it's proven or there's enough evidence beyond a reasonable doubt to conclude that I'm guilty. So in hypothesis testing, the null hypothesis is kind of like the innocent. We assume that it's true. We're trying to find enough statistical evidence to prove the alternative. Make sense? So when we look at hypothesis testing, again, there's three different things that alternatives that we can use to test. So oftentimes I give an example of driving to school. Okay, we use this in some of my earlier videos. And we found if we had a sample, let's say, of 30 students, and we found the average of those students, time it took them to get to school was 20 minutes, for example. Okay, with a standard deviation of 5 minutes. Okay? So when we collected this data, this was our descriptive statistics describing the sample. Now we want to use this to make some decisions. Let's say we don't think students drive very far to school, and we want to say we need, right now we have 10 minutes in between the class. We don't think we need that long. We think we can have it less than 10 minutes. So we may conduct a hypothesis test. Looking at our sample data, we have a point estimate. X bar is our point estimate, saying that it's 20 minutes. We could do a confidence interval to estimate mu, or we could do a hypothesis test. And one way to do that, we could say our null hypothesis is always what we assume to be true, that H0 is mu is equal to 10. And the alternative I'm testing is that mu, or the average that all Rhodes State students drive to campus, is less than 10 miles. So when we do our hypothesis, the null hypothesis will always have the equal sign in it. Okay? Some books will say it as the complement of the less than, where they'll show this as greater than or equal to, but it always has the equal. This book just tries to make it easier and just have it equal to. So the null is always equal to, and the alternative is what I'm trying to find enough evidence to show. This is called a left-tailed test. And the way I think of this is you look at the alternative and this inequality, it's pointing to the left, so that makes it a left-tailed test. So that's one type of test we can do, and there's 5 steps we'll do with each test. We'll do an example in a second. Now let's say I want to do a different test where I want to test if students drive more than 10 miles. This is a different type of test I can do. The null would be mu equals to 10. The alternative is mu is greater than 10. Since this is pointing to the right, this is a right-tailed test. The third type of test we could do is called a two-tailed test, and this is where we're just testing if it's different than 10. So the null is that the mu is equal to 10. The alternative is that it's not equal to 10. So there's 3 different types of tests we can do: a left-tailed test, a right-tailed test, and a two-tailed test. Now, when we do these tests, there's 5 steps we're going to do. Okay, and I'm going to follow these 5 steps in all of the hypothesis tests I do. So what I encourage you to do, when you come across a homework problem, whether you're doing it in WebAssign or the book, especially WebAssign, do the 5 steps and then go answer the questions on WebAssign, because they're going to break it apart and ask you little questions to each piece. But when I give you exam 3 in the final, I want you to show me all 5 steps. So practice doing these 5 steps. The first step is read the problem, establish the null and alternative hypothesis, and set the level of significance. In all of our homework problems, this is going to be given to us. And I can talk a little bit about what alpha stands for, but I believe Dr. Mosley does that in the lecture videos. We have to determine our test statistic. At this point, we're either using a z-test or a t-test. The difference between those, again, the z-test is if we know the population standard deviation or if our sample size is larger than 30. T-test, we do not know the sample size or the sample standard, we do not know the population standard deviation. So z-test, we know sigma. Okay? Step 3 is we draw a critical region and we make a decision. We either reject H0 or we do not reject H0. Step 4 is determining the p-value and compare it to alpha. 3 and 4 will give you always the same decision. If they do not, something went wrong. Step 5 is our conclusion. Okay? So, if we go back to the example I have here, and we'll just we're gonna do our right-tailed test. Let's say I want to test if students drive more than 10 miles to campus. So step 1 is setting up a null and alternative. So I'm assuming that it's equal to 10. And what I'm testing, I want to test. I made the decision, or you read the problem, it says, I want to test if students drive more than 10 miles to campus. So this is a right-tailed test. Okay? When you read your homework problem, it's going to tell you what alpha is. Let's say my problem told me alpha is equal to 0.05. That's called my level of significance. Okay? Step 2 then tells us determine the test statistic. Okay? So the question is, do I know sigma or not? And is my sample size larger than 30? I do not know sigma. I'm right at 30. Kind of borderline here. I'm going to go ahead and use a t-test. All the problems in your book, if you don't know sigma, they're going to use a t-test. That's fine. Okay, so I'm going to use a t-test. Okay, and Dr. Mosley goes through the formulas for those. So I'm going to show you the calculator. So we're going to go to our favorite button, Stat. Turn it on. Stat. Test. Now, instead of all the way going down to Z interval, T interval, we can just go right here at the top to t-tests. I don't have data, I have stats. Okay? This mu naught is whatever is in your null hypothesis. My mu naught is 10. Okay? X bar is 20. S is 5. My sample size is 30. And this is what type of test are we doing? Are we doing a two-tailed, a left-tailed, or a right-tailed? Mine's a right-tailed. Greater than mu naught. Okay, this should always match your alternative. And I calculate. And I get a t-test statistic of 10.9545. Pretty large. So I'll talk about that here in a second when we finish our steps. Step 3 was determine the critical value and make a decision. Okay, so step 3. Okay, on the critical values for the Z and T test, you're always going to draw a picture. Okay, the Z test and the T test are both symmetrical. Okay, now you're finding what's called a critical region. So where we get the critical region from is the alternative. My alternative tells me it's a right-tailed test, so my critical region is here in the right tail. If this would have been a left-tailed test, it would have been in the left tail. If this would have been two-tailed, it would have been both. Okay? And what we're going to look for is a critical value of t. Okay? Now, in order to know a critical value of free, we need to know what the degrees of freedom are. And I believe Dr. Mosley explains those, but those are always n minus 1. So in this case, our degrees of freedom is 29. Okay, where we get our critical value is from our t table. So we look at our t table. Up at the top, you can see it says one-tailed or two-tailed. Ours is a one-tailed, and these are the different alphas. Ours was 0.05. And you go down the side to your degrees of freedom. We go all the way down to 29. And down alpha 0.05, where those intersect, is 1.699. That is our critical value for t. Okay? So what we do now is we look at our test statistic. Okay? The t distribution still has a center of 0, so this is a positive 1.69. So if you'll notice in the t table, these are all positive numbers, so it is symmetrical. So if this would have been a left-tailed test, I would have flipped this over here and made it negative 1.699. Okay? But it's right-tailed. So now I look at where does my test statistic fall? When I determine the critical value, this region here I shaded is called the rejection region. So think of this as a number line. Wherever my test statistic falls, if it falls in my rejection region, my decision is to reject the alternative. If it falls in the non-rejection region, then I do not reject. So 10.95 is clearly way far to the right of 1.66, right? It's way out here. And I usually draw my test statistic up here. Clearly within my rejection region, right? It's probably further out. So my decision based on this is to reject H naught. Okay, and I'll explain what that means in step 5, so bear with me. Okay, now step 4 should give us the same decision. We look at the p-value and compare it to alpha. So where your p-value comes from is your calculator gives that to you. So our t-test statistic goes right here. The p-value is right underneath it. The p-value is a probability. So wherever this falls, the p-value is the area in the tail from the test statistic. So since 10 is so large, this is going to be real tiny. And it's always going to be less than 1. So when you look at p-value and you see this 4.0, if it's above 1, always look over here. It's in scientific notation. Times 10 to the negative 12. That means I have 11 zeros in front of the 4. So my p-value is equal to 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 4. Very, very small number, right? So our decision on the p-value is we're going to reject the null if our p-value is less than alpha. So in this case, my p-value is 0.006, 7, 8, 9, 10, 11, 4. The question is that less than 0.05? Clearly it is, right? So yes means we reject H naught. Okay, if it was not, then we do not reject. So our two decisions are either we reject H naught or we do not reject H naught, right here. Reject H naught or do not reject H naught. We never say we accept it. So it's kind of like the court system. When you're either guilty or not guilty and the jury finds you not guilty, that just means that they didn't have enough evidence to prove you guilty. No, in the court system, we never prove anybody innocent because you're assumed to be innocent. Same thing true hypothesis testing. We assume the null. We never prove it. We just try to find enough statistical evidence to prove the alternative. So in this case, since we rejected H naught, it's kind of like a guilty, we had enough